Okay, the next speaker is Soumen Sarkar. He will talk about on integral cohomology of weighted Grassmannian orbifolds. Please.
Thank you. I'd like to thank the organizer, and I'm happy to be here after a long time. And I was postdoc with Don Stanley. That time I didn't do that much work, maybe. So orbifold by orbifold, for me, at least for this talk, I mean, like we take Rn and quotient by finite space. Locally, it should look like that. But why this Grassmann? Okay, name maybe something like looks like Grassmann, but I was postdoc with Peter Vengroski. He said if we use Milnor manifold, Stiefel manifold, then why not Grassmann manifold? Why Grassmannian? So I like that idea. So from that, I am using Grassmann orbifold or Grassmann manifold. So if I say anything nonsense, please stop me and correct me. I think I will give the easiest and simplest talk in this meeting. So what is this? N by D matrices of rank D. So what is that pointer? Okay, here. So this collection of matrix we know from long time, and then we will say that okay, why only D rank matrices? Why not non-singular matrices of order D by D? So what are the connection between these two sets? So they are they have topology. Oh, not working. Since we have two sets, one is having good structure. Of course, both are having, but another is having group structure. So we can talk about whether we can define some action. So that action can give some identification. Or so that is the identification we know maybe from long time back. So looks very easy. The matrix A is identified to matrix B if they're related by this relation. So what interesting things it gives, the identification space or quotient space. It is called like Grassmann manifold, and in many places you will see that it has a smooth structure. Other way to think that we take n-dimensional complex space, and then we take the d-dimensional subspaces, a collection of d-dimensional subspace. So that is same as this set. Okay, so it's easy. So since we have quotient space, we can have quotient map. Then we can have topology here, because we know the topology here. This we can think as a subset of some Cn or something, C power something. So this is a topological space, and it is known that the dimension of this topological space is like sorry, this manifold is like d times n minus d, because if we take n by d matrices, the first d columns you can make like identity, and others remaining will give the variable things. So locally it will look like that. Okay, so the title was Grassmann orbifolds, how the orbifold comes. So what we did, actually Grassmann orbifolds, it was initiated sometimes back around 2002, I guess. Corti and Miles Reid, they studied through algebraic direction, and then Abe and Matsumura, they did this topological side. So, and Abe gave a talk in 2013 in Osaka toric topology meeting. So the description I will just say. So what they did, so this Grassmann manifold, they consider there is a nice embedding from this Grassmann manifold to some projective space, and then they pull back it, and then they define the weighted sister action on it, and they said that is the weighted Grassmannian orbifold, or weighted, yeah, or Grassmann orbifolds. But so I told my student Kaushik that maybe we can study this sorry, Grassmann orbifolds. And in the talk, Abe discussed like cohomology ring, but with rational coefficient. But rationally, it looks like similar as this one. Of course, the group structure, so that means ring structure is a little bit different, but they are almost similar, which made me like a little bit. For the previous one.
What was the equivalence relation?
That just multiplied by the t.
So why?
So
So
because
that's the usual Grassmannian, right?
yes, usual Grassmannian.
Did you tell us what the Grassmannian orbifold is?
Of Abe and Matsumura, how they defined. So they took the Plucker embedding in some CM, projective space, PCM, and we have this natural sister fibration. So they took the sister fibration and okay.
Oh, so I thought I missed the definition. Maybe you didn't.
No,
Yeah,
I
okay,
will
sorry.
give another
Sorry.
definition. But that's what I wanted
Very
to
good.
say.
Thank you.
Okay.
Sorry.
Sorry. So Kaushik didn't. He found something, so he used this idea and twisted the definition. And it took us some time to. But why I was interested? So Tony and Nigel, France, they had a good paper on cohomology of equivalent cohomology of weighted projective spaces. So weighted projective spaces, it was done by Kawasaki long time back, and he showed that it has no torsion. The cohomology of the weighted projective space has no torsion and concentrated in even degrees. The interesting part was the computing the equivalent cohomology ring structure, and it is, even though it is like as a cohomology group, it is similar as CPN, but the cohomology ring structure was very difficult. So that part I liked it, and I wanted to see that what will happen for other orbifold case. So Tony, John Beck, and I, we have some other results related to toric orbifolds. But here I will discuss about the interesting part is, so why integer coefficient? So we had a talk by Juliana. She was taking the complex coefficient, but if the ring structure are different, so that will say that they are not homotopic. Right? If the ring structure not isomorphic, then that will say that they are not homotopic. But that cannot be captured by rational coefficient or complex coefficient. So that's why I'm interested in integral coefficient, because many of us are like homotopy theorists. Right? So okay. So we just restructure the matrix like this way for our purpose to see this. Now we want to do the identification. So some group action here. So T is coming from GLD, and we take this weight W1, W2, Wn, and some positive integers greater than or equal to 1, and we define this identification. So this A and T has relations. So since T belongs to sister, we can talk about this power, and the determinant of T has to be like this. So if we take that, we get a quotient space, and that quotient space we said that it will be called by Grassmann orbifold. So now we have different definition than Abe and Matsumura. So it took us little time to prove that they are same. Those two objects are same up to something. So if we notice this, since it is n by d matrices, this collection of n by d matrices. So if we take the diagonal n by n matrix, it acts very nicely. So that action goes through the weighted projective space, weighted Grassmann orbifold. Where is that? Okay, so that is very natural, it comes. So with respect to this action, we will see that what is happening. So we can prove that we have some orbifold structure, and the orbifold structure, the orbifold open chart can be chosen like the sister invariant. So it says that rationally it is similar as Grassmann manifold. Okay. Okay. So what about some other properties? Now, what we want to do, so the question comes, since it is Kawasaki said that if we take weighted projective space, the cohomology of these spaces are having no torsion, and it is concentrated in even degree. Can we expect the similar result here? So Kaushik and I tried to do that, but at that time we could not do it. And before that, we have paper of Tony, Franz, and Nigel, and also another paper by Nigel, Megumi, and Tara, and Gareth. So what they implemented, the concept of divisiveness. So that was a good concept to apply. See, if we consider the divisive weighted projective space, then we can give nice cell structure. So Kaushik and I did some similar concept using some technique. So we said divisive weighted Grassmann orbifold, where we can give the actual cell structure. However, there are many other Grassmann orbifold which does not satisfy the divisive condition. So divisive condition, I will not say what is that, but here we will see that much more generally we can say something. So we will not use this object too much, but it will help in some sense. Okay, so for this Schubert symbol, what we can define? So given this weight, we can define some other positive integers. So that we say Ci. So if we have that one, then we can define some equivalence relation on this set. So if we forget the 0 and we know this definition from long back, and what it gives weighted projective spaces of Kawasaki. So the weights are like C0, C1, Cm, and the map, the orbit map, we just say that it is denoted by this one. So we'll see simple technique can lead something good. So we denote the coordinates of the weighted projective space by this one. So as I told you, my talk will be very simple. So it's many things everybody knows. Okay, so now we have another new object, right? So it was like weighted Grassmann orbifold, and this is now weighted projective space. So dimension looks like a little bit different. This is M and then this D. So here we have natural sister M action, right? And now the sister action, how it is coming? It's coming via some embedding. So what was there? N by D matrix. So these are like D columns. So we can take the wedge. So we can we can get a map from set of all N by D matrix of rank N to Cm plus 1 minus 0. So we take that matrix and then we can quotient it. So via that map, we will get a sister N action on here. Okay. And already naturally we have sister M actions. So what are the relation between these two actions? It's like they commute. Very naturally, we can just check the coordinate wise and we'll see that they're commuting those two actions. Okay. Okay. So for Grassmann manifold, we have natural this embedding, which is known as Fluker embedding. Here, what we can get also this from the weighted Grassmann orbifold to weighted projective space. So natural embeddings are there. So, and interesting part is this is equivariant. So equivariant in the sense like this sister N action on here. Okay. So already we noticed that sister N action on weighted Grassmann orbifold, and here the induced sister N action here. So with respect to that action, this is equivariant embedding. Okay. So, okay, another well-known things which we know. So what we defined this pi c as the orbit map, right? And C was some corresponding to this vector. C means like this C0, C1, Cm, some vector. So what about if we multiply this weight by some positive number r? So that means pi of Rc, so that map. So if we consider that map, so actually what we should get? We should get weighted projective space with weight Rc0, Rc1 up to Rcm. So now two objects are there, whether these two objects are different or same. So it says that no, it's good. It is well known from this can be proved by algebraic method as well as topologically we can show. So they are nothing but same, equivalent. There is an equivalent homeomorphism, and it helps to say that okay, whatever weight vector we take, we can consider the GCD of that weight vector is 1. So then it's a it was helpful in Kawasaki's paper, so we are just going to have it. So as a result, if we forget jth coordinate, so that means jth coordinate is 0, and if we take something else here, then this pi c, this will be the set here, this will be homeomorphic to this one. So what is R? R is GCD of the remaining one. Okay, so the image of this set under this orbit map is same as this one. So what it is saying, even though as a orbifold the singularities are more, but as a topological space we are killing the singularity when we are forgetting the one hypersurface. Okay. Now I will be little bit sloppy maybe, but this I will understand. We will understand when, how, and when it is coming in the next slide. So we take odd dimensional sphere and we say that okay, G will take a finite subgroup of SON, so naturally it acts there as an orientation preserving action. And we are considering that this hyperplanes cut like invariant. So if we have that, now up to k, 1 to k is a set, so we can consider the subset of that one. So we'll say that k1, k2, kn, and this we denote by sigma. We said, okay, take all kind of subset, and we denote it by L. It's a little bit notational slide, but it helps. So we define a subset of S 2k plus 1. So this contains set of all Z1, Z2, Zk such that this relation happens. So what I mean, it's like we take Cn, C1 copies, and we take the unit vector and we forget some of the points that they are zeros. So that can be like a sphere. If we forget one, if we take one coordinate is 0, so we get codimension 2 sphere there. So we take union of some of these kind of spheres, not the one sphere, but some of several spheres. So that set is geometrically represented by. So this is not the sphere, but union of some spheres. So which is invariant by that group action, G, finite group action G. So what we get, this one. So this one was this is a consequence of some well-known result by Broden or somebody, but we also discussed in this, Tony, John Beck, and I. So, so if P and mod, I mean order of this one, they are co-prime, then this has no P torsion. So why it is important? Because I want to make my Grassmannian as a sequence of co-fiber, or I can obtain that sequence of co-fiber where I need this space, map from this space to that one, so to make the mapping cone or co-fibration. And as a result, I can get that as a cohomology group, this has no torsion. So why it is that? So if we start, so in the beginning, we noticed that we have an embedding, right? So equivalent embedding to some weighted projective space. and that weights we can take as a GCD is 1. Right? So if we take a prime P, then we will get some CIs which is prime to P. Right? So we'll take that point and we'll take the complement of that set. Right? So that point will give one kind of cofibration. So it will remove one, what shall I say, weighted CP, suppose weighted P C0 to Cm, and Cm is the coprime to P. Then we can forget the last coordinate. So we'll come to the next. So in this way, we get the cofibration. Okay. And successive application of cofibration and using the previous result, we can prove this one. So, and moreover, we can say that as a cohomology ring, it is concentrated in even degrees. So with no tension as well as it concentrated in even degree. The proofs are different, they are not same. So we have to apply different techniques for that. Of course, what I want to say that this was proved for this, and this paper made me like, I mean, inspired me that to find out, or not only this paper, but you know, in GKM, famous GKM paper, Goreski, Kuti, Sakma, and McPherson. So most of their theorem, they assume that what cohomologies are 0. So I was a little bit surprised that why we need to, what are the spaces exist where the odd cohomologies are 0. Right? So if we don't have anything, any existence, then it does not make sense. But for manifold case, of course, there are many examples, but can we have such kind of examples for orbifold case? So why this thinking came that again, Tony and Matthias and Nigel, they gave some nice representation of equivariant cohomology ring for weighted projective spaces. Because it has no odd degree cohomology and it concentrated in even dimension. Okay. Any question? Is it okay? No, that's important because so what we did, we make like it's not cell structure kind of things, but some subset of weighted projective space which we can embed in some Cm, weighted what I denoted by WP some weight. Suppose Ci up to Ci, the next step is Ci plus 1. So therefore, no restriction. So this is good for Grassmannian case, because if the embedding is in such a way that if we forget one orbifold cell from weighted projective space, then the remaining, in the remaining case, for weighted projective space, it is lower dimensional weighted projective space, but the remaining subset here, it may not be orbifold. It is like, you know, union of some orbifold, but we can handle it because of the cofibration construction. And the result, I said that if we come to the lower dimensional weighted projective space, the order of singularity topologically we can reduce. So that helps. Yes, additively it is same as Grassmann manifold.
Yeah.
So my question was, is the cohomology of weighted Grassmannian, is it additively the same as the usual Grassmannian?
It's like if we, by additive, I feel like you mean we establish something, right? If we fix the ith cohomology, then additively it is same. But the interesting part here, it was shown that the cohomology ring structure is totally different. It is not generated by one element. It needs more generators. Okay. So thanks to Professor Masuda to mentioning this GKM theorem and many others. But whatever we are going to discuss this, I think this concept was initiated by Gulamin Zara, and then my lovely friends John Beck, Shintaro, and Alistair, they generalized it for toric orbifolds. So, oh, here, yes, their names are here. So, what we want to take, we want to take a graph, a regular graph, and it has some we can, of course, on edges we can do the orientation cases, but still I am assuming it, and it should satisfy some interesting conditions. So there should be a map, which we say like axial map, and it satisfies something. So something means if we take this EP means P is a vertex and edges are coming from the vertices. So this set of edges are denoted by EP, and on each this edge we have this map. Right? So this pairwise, they are like linearly independent. That condition is there. Plus, what restriction we have? So very nicely they found this relation that so for GKM graph for manifold, this RE and RE bar, they are 1. However, here they may not be 1. So for the orbifold case, it is little different. But this is a very nice restriction. So if we see the image of this map, it is in BTN with a Q coefficient. And this relation, when we are taking, it is in Z coefficient. Okay. Okay, so moreover, if we have this kind of thing, so what it is saying, if we have edge, this is P vertex connected by some edge, this is Q vertex. So here we have some collection of edges, here we have some collection of edges. So we should have the map from here to here, which is satisfying this condition. Okay, so SE means source and target we denoted by this, so it should satisfy this condition. Okay, so this is, yes. 1.2. Wait. Okay.
Can I have a condition for 1.2? Actually, for the user GKM condition, the actual functions for the opposite edges are exactly different by -1.
Yes,
And
because
do you allow +/-1 sign over there?
they are opposite.
They should be opposite.
Actually, most of the case, the calculation, whatever I did, it came opposite sign.
But do they allow the same sign for
Same sign.
the opposite directed edges?
They are, you know, it depends on the orientation, but we allow that one. It comes.
Oh, I see. Thank you.
But I will give one example. So little bit combinatorics, very easy, the boundary of a square, and we are having some this map. Yeah. So we have to be little bit careful to say that, so if this plus several relations, if it is satisfied, then we can say that this alpha is an axial map there, it satisfies it. And this map also satisfies the remaining conditions. Okay. So therefore, it comes the definition, combinatorial definition of some rings. So what we are taking, we are considering set of all maps from here to here. So that means some elements here. But now we restrict that, okay, so what happened for the GK manifold case? So if we have an edge, so this is fixed point. So fixed point that has a tangent space. So since it is a fixed point, we will have that tangent representation of the torus on the tangent space. And since it is complex, so we'll have one-dimensional representation. So each edge will represent that representation, right? So it will give some torus action on the sphere bundle. So that means circle bundle corresponding to this line bundle. So that means it is a character. So that character gives the axial map. Right? So, but here, this is not exactly that character, but multiplied by something. So if it happens, so what is this RE alpha? So what happens for the orbifold case? Oh, maybe in the next slide it may come. So combinatorially, this RE tilde, it comes from the definition we said here. So if RE alpha is satisfying, then if we multiply by some positive number, they also satisfy the relation. So what we want to take? The minimum one in the definition. Okay. So this has a ring structure, and that is called like equivariant cohomology ring for corresponding to this GKM orbifold GKM graph. Right? Okay, it is denoted by this one, and I should say something about the orbifold GKM orbifold. So in this paper, or they also have some other papers, so they discussed this orbifold GKM object or GKM orbifold spaces, and precisely what they consider. So this is the first case, but they discussed many other cases also, and they associated some study of GKM orbifold and some geometric object or notion called curvature, which we don't want to go. So it's a similar definition, many of us we know, but let's recall. So it will have the finite fixed points, and they are discrete, and the one-dimensional orbits, union of one-dimensional orbits, as it will be like union of spindles. So it's not CP1, but it is weighted CP1. So with two weights. Of course, homeomorphically CP1 and weighted CP1, they are same. However, if we see their Chan classes corresponding to that point, they are different. Okay. And it satisfies this one. Okay, now here I have to say a little bit. So how we get these weight vectors. So if we take a point, so that is orbifold point now, so it will have an invariant neighborhood, which we can pull back to the manifold case, and that pullback, what they showed that there is a like a manifold chart, or sorry, orbifold chart. So that will be like on the top it is a manifold, and on that manifold it is not Tn action, but a finite extension of Tn will act there and having the same fixed point. So therefore we will have the tangent space of that manifold. Is we can have the similar expression here. So tangent space there, it makes sense, and it will be like it can be expressed by one-dimensional direct sum. So this will be, I mean, representation will be one-dimensional. Now, so since the group action here is like a finite extension of Tn, therefore we will have a map from the Lie algebra of this finite extension to here. So the character we are getting here, so that character will map here, and that image is like alpha 1 to alpha n. And if they are linearly independent, here we will get the linearly independent, because this is a finite extension. Okay, so that's why we get these weight vectors, the irreducibility representations. Okay, so what is the relation between this GKM orbifold and Grassmannian orbifolds? So it's like we can show that for this Kaushik did some calculation in our paper, and that helped me to prove this one also. So explicitly what we can do, so it is the fixed point set for the Grassmann orbifold is like it corresponds to if we take the permutation matrix that gives the fixed point set, corresponds to the fixed point set. And if we take two permutation matrix, different permutation matrix, and we can see that when this they have edges, and on that we can get exact and how we can compute how the truss is acting exactly. So from that, and those vectors satisfy the definition of this GKM orbifold and GKM graph. Okay, so moreover, what I can do for Grassmann orbifold case is it is having invariant TN CW structure and odd vanishing. Therefore, I can have this result that if we have weighted Grassmann orbifold, then the equivariant cohomology ring is isomorphic to this one as BTN algebra. So this is due to the result of Alistair and John Beck and Shintaro. So,
you mean Grassmann orbifold there, don't you? You don't mean weighted Grassmann orbifold.
oh, sorry, this typo. Oh, thank you. Oh, that's easy. Weighted Grassmann orbifold. It is known result. It will be, sorry, this is a typo. Yes, this is weighted Grassmann orbifold. Oh, Grassmann orbifold. Okay, Grassmann orbifold. I have to say weighted Grassmann orbifold. Otherwise, thank you. I guess, yes, that is the thing I wanted to share. However, as I told you in that weighted projective space case, the ring structure, computation of the exact ring structure is difficult. Here also it's difficult. Thank you.